So here we are going to take a look at a few tests and strategies for determining the convergence of series. In other words, does an infinite series approach some number, or does it head off towards infinity, or does it do some funky business? And so there are really, three things that we want to think about. We want to think about geometric series, which should be a review from previous courses, and then talk about the integral test, which is connect back to improper integrals, and then talk about p-series, which are also going to connect back to improper integrals. So let's remind ourselves that a geometric sequence is a sub n equals a sub 1 times r to the n minus 1. This is for n is greater than or equal to 1, right? And we know that r is the constant ratio. So basically what we're looking at is that you're multiplying by r each time, and it's really an exponential function, but in sequence form. Geometric series is simply the same thing. A finite series would be S sub n is, say, the sum from k equals 1 to n of a sub 1 times r to the k minus 1. And we could also have an infinite series that goes from, say, n equals 1 to infinity of a sub 1 times r to the n minus 1. So this is maybe the most likely scenario that we're curious whether this thing converges. So let's just investigate and remind ourselves how to find the sum of a finite or infinite geometric series. So writing out a few terms here, we would get S sub n, this is the series, is equal to a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r cubed plus dot 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 plus a sub 1 times r to the n minus 2 plus a sub 1 times r to the n minus 1. So that comes straight from this formula, right? We are plugging in k equals 1 and getting a sub 1, then plugging in k equals 2 and getting a sub 1 times r, and each time we're just multiplying by another r until we get all the way up to n minus 1, and we have this whole situation. Now, if I multiply this equation by r, I would get r times s sub n equals a sub 1 r plus a sub 1 r squared plus a sub 1 r cubed plus a sub 1 r to the fourth plus dot 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 plus a sub 1 r to the n minus 1, because I'm multiplying by r here, plus a sub 1 times r to the n, because I'm multiplying by r here. So I just multiplied everything by r. Now, if I take the first line, s sub n, and subtract r times s sub n, so this minus this, everything is gone except for a couple things. A sub 1 and a minus a sub 1 times r to the n. Everything else is going to subtract. So I just end up with the first term minus a sub 1 times r to the nth power. So that means that factoring s sub n times 1 minus r is equal to a sub 1 minus a sub 1 times r to the n, which means that s sub n is equal to a sub 1 minus a sub 1 times r to the n divided by 1 minus r, or a sub 1 times 1 minus r to the n divided by 1 minus r. So this is your partial sum of a geometric series. A sub 1 times 1 minus r to the n over 1 minus r, and we just developed that from that formula. Now, if you think about taking the limit as n approaches infinity of s sub n, you would get the limit as n approaches infinity of a sub 1 times 1 minus r to the n divided by 1 minus r. And this will approach a sub 1 over 1 minus r if absolute r is less than 1, right? Because if r is less than 1, if absolute value of r is less than 1, then this thing is just going to go to 0 because you are taking a fraction and multiplying it by itself a bazillion times. So that just goes to 0, and so you just end up with a sub 1 over 1 minus r. So provided your ratio, your constant ratio, is less than 1, your sequence will end up going to a sub 1 over 1 minus r. And the only thing you need to watch out for a little bit is if you don't start at 1, then this can be a little bit confusing, but you can sort of figure it out from there. So here is your infinite geometric sum, provided r is less than 1. Here is your finite sum, no matter what r is. It doesn't matter. It will always go to this. So let's look at these two geometric series right here. It says, how do we know they are series and not sequences? Well, because there's plus signs. This is a sum. This is a sum with some negatives as well. Find the first 4 partial sums, then decide if the series converge. If they do, find their infinite sum. So I'm just going to look at this example and let you do this one. So the first partial sum, s sub 1, is 1. The second partial sum is 1 plus 1/2, which is 3/2. The third partial sum is 1 plus 1/2 plus 1/4, which is 3/2 plus 1/4, which is 6/4 plus 1/4, which is 7/4. The fourth partial sum would be 7/4, which is the third partial sum, plus the next term, which was 1/8. 7 times 8 is, oh goodness, it's some number. 6 times 8 is 48, plus another 8 is 56. So 56/8 plus 1 over 8 should be 57/8, I believe. This is not looking good. It feels like these are getting bigger, unless I made an error here. But maybe I didn't make an error, or maybe I'm just not thinking correctly. That's definitely 3/2. And 3/2 plus 1/4, 6/4 plus 1, that's 7/4, and 7/4 plus 1/8. Oh, I don't need to be multiplying by 8 here. I need to be multiplying by 2. That's embarrassing. So this should be 14/8 plus 1/8, which is 15/8. Okay, that's a little bit different. So the constant ratio, what we are multiplying by each time, is 1/2. So this looks like the sum of a sub 1, which is 1, times 1/2 to the n minus 1, from n equals 1 to infinity if it kept going. So in fact, my constant ratio is less than 1, and therefore it should converge to this. So a sub 1 is 1. It will be converged to 1 over 1 minus 1/2, which is simply 1 over 1/2, which is 2. So this is going to get closer and closer to 2. 15/8 is already pretty close, but when I add 1/16, it will still be less than 2. So here I will let you follow a similar process. So I'll look at a couple of these examples, but not all of these. It says, important for you to recognize geometric series, as there is an easy rule to tell whether they converge or diverge. Which of the following are geometric series? Assume n goes from 1 to infinity. If they are geometric, what is the common ratio? Can you determine whether they converge or diverge? What would they converge to if they do converge? So I will just pick 1, 2, 3 of these to look at. So this one, 3/2 to the n, that definitely looks like a geometric series. We could write it as, say, the sum from n equals 1 to infinity of 1 times 3/2 to the n. Now it's a little bit different because it's not n to the n minus 1, but it really doesn't matter. But my first term here is not 1. My first term is 3/2, because if I plug in 1, I get 3/2. So If this were going to converge, I'd have to consider about that. But since the constant ratio is 3/2 and that is definitely greater than 1, this thing is going to diverge. Okay, let's come down to this one. -1 to the n. Is this a geometric series? Well, yes, because it is of the form a sub 1 times r to the nth power, where r equals -1. But the unfortunate thing about this is that when r equals -1, I'm actually wondering if r cannot be -1 with a geometric. Kind of forgot that. But with r equaling -1, we know that this is going to diverge because, unfortunately, if we look at the partial sums, we would have -1, then we would have 0, then we would have, right, because it would be -1, then -1 plus 1, then we'd have -1 again, then we'd have 0, then we'd have -1. So this is not converging to some number. Okay, coming down to this one, we need to do a little business here to say, you know what, this right here is going to be 3 times 1/5 to the n, right? 1/5 to the n is the same as 1/5 to the n. So yes, this is geometric. And in fact, r is equal to 1/5. 1/5 is less than 1, which means that this is going to converge. Great. So let's find the first term. If we plug in 1, we get 3/5. Dividing that by 1 minus the ratio, we should get 3/5 over 4/5. Multiplying by reciprocal, we get 3/5 times 5/4, which is 3/4. So it looks like this is going to converge to 3/4. Sometimes you can do a little bit of manipulation to figure out where that thing is going to head. Okay, moving on here. Here's some more general stuff. So we can see if the sequence S sub n of partial sums converges to S, so the limit as n approaches infinity of S sub n equals S, then we say the series converges and that its sum is S. We write this. If it does not exist, we say that the series diverges. So we already kind of know that. Some properties. If both of these things converge and k is a constant, then the sum converges. If we multiply by that constant, it still converges. Changing a finite number of terms in a series does not change whether or not it converges, although it may change the value of its sum if it does not converge. So if the limit as n approaches infinity of something does not equal 0, or it does not exist, then this is going to diverge, right? If you're going to add up infinitely many things, and this is pretty important, that thing has to approach 0. So that should always be your first check. Does the sequence that I'm summing up approach 0? If it doesn't, if not, then your series is definitely going to diverge. The only way for you to add infinitely many things and have them approach a finite number is if those things are getting small and getting small really, really quickly. Okay, so let's look at a few things here. We could find, this is a geometric series that converges. This is a geometric series that converges. So this is going to converge to whatever these two converge to, which we should be able to find. This is simply a geometric series that's been multiplied by some number, so we could pull out that -18 if we wanted to, find what this converges to, and then multiply by -18. This right here diverges, -4/3 to the n. That's a geometric series where r is greater than 1, so this is still going to diverge even though we multiplied it by 18. It doesn't matter that we started at 200. Yes, it's going to change what this thing converges to, but it will still converge, even though we started at 200 instead of 1. This right here, well, I'm not really sure what this one is trying to be showing. But this would be the same, I suppose, as the sum of 2 plus the sum of 3 over n. And that's going to diverge, so we kind of know that this whole thing is going to diverge. And I guess what this is trying to show is, hey, the limit as n approaches infinity of 2n plus 3 over n does not equal 0. It equals 2. So the sequence itself heads towards 2. So because it doesn't head towards 0, there's no way that this series will converge. And this one right here is, well, be careful. Because yes, the limit as n approaches infinity of 1 over n equals 0, but I don't think that this thing converges, which is a bummer. Okay, so those are a few sort of properties of those. Okay, so I just want to look at this one more thing here. Now this video is getting a little bit long, but let's just talk briefly about a couple more strategies for determining whether series converge or diverge. So let's consider the harmonic series, which we say 1 over n. The reason it's called the harmonic series is because when you sing, say, a C, like that's probably not a C, but it's a note. Then when you sing that note, there's also the octave above that's also sounding. Bum, bum. And then above that, you hear the fifth. Bum, 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 bum. That's a third, so a fifth is here. Anyways, all those notes are sounding and their wavelengths depend on a series that is like, oh, you started with 1 and then your next one is half as long and then your next one is a third as long and your next one is a fourth as long. So I know you really loved hearing me sing that, but I'm in a choir, no big deal. Actually, I dropped out, never mind. But anyways, that's why this is called the harmonic series. And then its sibling, 1 over n squared. So do we think these things converge or diverge? So this sum right here, that is the ugliest sum symbol I've probably ever written, of 1 over n is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus dot dot dot. Now let's draw that geometrically. 1 looks like that. That is 1. 1/2 looks like that. That is 1/2 because this function right here is 1 over x. So if this is 1 over x, then that's 1/2, and that area right there is 1/2. So this is 1, this is 1/2. This right here is 1/3. This right here is 1/4. So we can see that this is actually just a Riemann sum for the integral from 1 to infinity of 1 over x dx. Oh my goodness. It's just a Riemann sum for this integral. And this is 1 over x squared. So drawing some things on here, that right there is 1. The sum, goodness, of 1 over n squared would be 1 plus 1/4 plus 1/9. Here's 1/4. Here is 1/9. And the next one is 1/16. Well, this is just a Riemann sum for the integral from 1 to infinity of 1 over x squared dx. But having drawn that, I wish I'd drawn it in a different way. I wish I had used this height here, and then this one, and then this one, and then this one, because then it would look like it's less. So we can see that this Riemann sum is bigger than this, but we know that this diverges, which means that this diverges. If we draw this in the right way, which we can, we know that this converges, but the Riemann sum will be less than that as long as we draw it on the right side in a certain sense. So then this converges. So basically, what the integral test tells us is that if the integral from 1 to infinity of f of x dx converges, then the sum from n equals 1 to infinity of a sub n converges, provided a sub n and f of x are the same thing in function and sequence form. But if the integral from 1 to infinity of f of x dx diverges, then the sum from n equals 1 to infinity of a sub n also diverges. I probably could have explained this a bit better, because really what I'd want to do is say that this sum right here is it's less than 1 plus this integral. And since this integral converges, and then if we just add a random 1 to it over here, it really doesn't matter because it's still finite. And so this is going to converge as well. So that allows us to say the p-series test, which is the sum from n equals 1, whoopsie daisy, to infinity of 1 over x to the p, n to the p, converges if p is greater than 1, diverges for p is less than or equal to 1. And this comes straight from the rule that we developed about the integral from 1 to infinity of 1 over x to the p. So now we know if we have something raised to a p power, it converges in the denominator. It converges if p is greater than 1, diverges for p is less than or equal to 1.